Let me spend a few minutes and tell you really, I told you something about making materials. Let me tell you about the other thing, which I suppose in this place is more important. The second topic should be how to shrink City University down to a chip, right? At least some of the labs. How can you make a whole laboratory on a chip? Let me show you that doing this, first of all, makes sense. Secondly, is possible. And thirdly, allows you to do all kinds of new things. So what does that mean? Well, what it means is normally when you do an experiment, and you want to do a lot of experiments, what you do is you use a plate like this. It's called a microtiter plate. And this particular one has 384 little wells in it, 384 small wells. And each well you could easily fill, say, with 100 microliters of fluid. And this is called a microtiter plate. And you have robots that have pipettes that go and take fluids and mix them and combine them. And you do this 384 times, and you do many of these plates. You can do as many as you want. What we do is replace each of these wells by a drop. So rather than using the drop to template things, we use the drop to encapsulate things. And so inside of the drop is our test tube. The fluid on the outside is a completely inert fluid. We use that only to control what we do with the drop. So we separate the experiment from the fluidics. The fluidics is controlled by the outside. We don't care about. The inside the drop, is the experiment. And the difference, the reason why this is important is one of these drops has about a picoliter of volume. A picoliter compared to 100 microliters is about 8 orders of magnitude. So you're doing every experiment in a much smaller volume. That's why it's so important here, right? You're shrinking the volume. So here's a few rules of thumb, a few numbers. If I have a 1 micron diameter drop, that's a femtoliter. 10 microns, that's a sweet spot for us, is a picoliter. 100 microliters is a nanoliter. We're doing this at 1,000 experiments per second, 1,000 drops per second. Just to give you a sense of this, if I take one molecule and I put it in a 1 micron drop, that's a femtoliter. 1 molecule in a femtoliter is a nanomolar concentration. Nanomolar concentration is the concentrations that good catalysts, such as enzymes, operate at. And so you actually understand why you do this very well. If in a cell nucleus is about a micron in diameter. Why is it a micron in diameter? So chemical reactions, which take place all the time in the cell, all the chemical reactions that take place in the nucleus of the cell that propagate information through the replication of the DNA, through the translation of the DNA, all of that has to happen very high probability, and you do that by restricting the volume so the concentration is large. So you can do the same thing here. And here's why it's interesting. So imagine you go to, for example, a big drug company, and they use these robots to do screening. But here's the problem with the screening. So imagine a typical drug company. They will have thousands of compounds that they've made over the years, and if they find a new biomarker for some disease, the first thing they say to develop a drug is, why not try all the compounds they've already developed? They've put all that money into it. Why not at least test that? So they might want to test, just does it bind to that biomarker? So imagine they have a library of about 100,000 compounds, and this is very typical for many drug companies. And they want to measure an absorption, an IC50, an absorption coefficient. They might do 10 concentrations of each. Well, that's 1,000,000 different experiments. So you're doing 1,000,000 experiments, but if you do it even at 10 microliters with one well, 10 microliters per test, 1,000,000 experiments is 10 liters of reagent. 10 liters of reagent. And if you ask any drug company, what limits the number of screens that you can do? It's the cost of the reagents. The reagents are just too costly. Each experiment doesn't use very much, but they're doing millions of experiments. And you can scale this now. The best ones do smaller drops, but still the limitation is always the amount of reagent. And then you might ask, well, if I have a robot, and I sort of calculate, I have a robot, 8 pipettes, I do 3 times like this, I do 1,000,000 experiments, how long does that take? Well, it takes 4 months running 24/7. Don't sleep. Make sure that robot's running. Make sure it doesn't break, because it has to run for 4 months straight. You can do that. And drug companies will do that. But if we do it here with microfluidics, if we use a picoliter per experiment, 1,000 experiments per second, then the whole experiment takes a microliter. One experiment is less than a single test. You want to do 10 times, it's still only one test. And the whole experiment, if you do 1,000 per second, the whole experiment is done in 20 minutes. Go out, have a cup of tea, come back, and it's all done. So can we do this? Well, we have to set up to be able to mimic the robot. So here's the way we've developed. These are the tools we've developed for manipulating drops. We can make drops. Here's just some way of making drops. We can split drops if we want to do assays, 2 assays. Here we're taking drops, we're splitting them into 2, the same size. Here we're splitting them into different sizes. Maybe the contrast is a little bit better here, the different sizes. We can split them many times. Here we're splitting these large slugs into 6 times to make lots of drops. We have to mix them together, so we have to add drops. Well, we can do that. These are an electric field. Remember, these are water drops. Typically, we're going to do water and oil. So they're water drops in oil. Water has a high dielectric constant. Oil has a low dielectric constant. I put an electric field across something with a high dielectric constant. That induces a dipole. I have a pair of dipoles. If the electric field are in the same, they're 2 dipoles like this. They attract. So you see they always coalesce when they come close to the electric field. Here's something new we invented. We call this a pico-injector. Here we're literally injecting a picoliter of fluid into each drop as it goes by. And this is, again, controlled by electric field. So if we have 3 pico-injectors, 1, 2, 3, the electric field is on only here. So this is the only one that's injecting. And we can control it. So now we can mix and match on a drop-by-drop basis. Of course, you have to detect. We can detect. You use optical detection. I won't go through the details. It's very simple. And finally, if you really want to do a screen, you want to select the ones that you really like. So we built a really complicated device. We built a sorter. This has a detector. And this now, we put an electric field. Remember, electric field induces a dipole in the drop. And a dipole in electric field only orients. But if you put a gradient of electric field, you put a force on it. So this turns on a gradient electric field, and you can see we can separate the dark from the light drops very easily. You can do this 1 drop in 5,000 per second. So now